Okay, so briefly, we will start this session for the week first of fundamentals of nano and quantum photonics. And as per the protocols, we have to introduce ourselves every time we are having this session. We are having this weekly session. So I'm Shazam Bhatt, and I'm a direct PhD student at IIT Bombay and TU Berlin. And I work in the Institute of Solid State Physics as well as Applied Quantum Mechanics Lab. So this is kind of my area I work on. I don't directly work on quantum photonics, but I work in photonics, I work in optics, I work in solid state devices. So this course is definitely being offered by Professor Naresh Imani of IIT Hyderabad, and I guess he's the best person to teach this course because he's having his background in this particular field. So what we are going to do, the way I teach or the way I take the sessions is a little bit different. If someone maybe who might watch the lectures over the YouTube later on, they might be knowing me from my previous sessions on, let's say, the fundamentals of device physics and the microwave devices. So I've been the teaching assistant twice before this particular course, and the my goal is particularly to just brush up whatever the professor has taught in the entire week. Obviously, we are not going to cover the entire material in just 2 hours of session, but I try my best to just incorporate certain few things which are very essential to solve the problems or to have the at least the basic understanding of this particular subject. So, having said that, the essential goal is basically to give you at least a flavor so that you can correlate it with certain basics you have already understood. So what do I mean is that, let's say, for example, some of you might be maybe studying electronics. Most of you are from electronics background. And if some of you are from undergraduate, then these particular courses are not, at least in undergraduate levels. We are not taught the photonics, at least in undergraduate, at least up to maybe second or third year. So what I try to do is that I try to relate it with the, I should say, semiconductor device physics. I try to relate the how you can understand photons, electromagnetics in terms of the already studied concepts in, let's say, semiconductor physics. Let's say if you know how the electron behaves in a lattice, then you know how, let's say, for example, electron as a wave behave inside maybe let's say, for example, a quantum well. If you don't know any of these words, you don't need to worry about it because I'm going to just deal with it. And that is particularly my goal, that to simplify certain complex concepts so that you can understand them from the basic point of view. That will be the entire goal of my sessions. And definitely, then there are those question answer sessions, questions which we need to solve by the end. So my goal will be approximately 1 hour or 45 minutes of brushing up the main concepts or the basic concepts. It might include basic device physics, electrostatics, electromagnetism. Maybe then once we go into the later part of the course, then it will be some basic quantum mechanics. So then later on, and in the second half of the 1 hour, we will be trying to solve the some of the basic questions which are basically asked in the quiz in the last year. So that is basically our goal. So if we talk about the course layout, so this is the course layout you might have seen on the NPTEL portal. You might have seen on the NPTEL website. So this is given at the introductory lecture in this particular course, fundamentals and of nano and quantum photonics. So most of these things are pretty new to you. I know, particularly the nanophotonics part. Maybe some of you have studied about the electromagnetics, Maxwell's equation, a little bit of wave optics, electromagnetic radiations. Not much about the evanescent waves. We are not taught about this in our maybe 10 plus 2 level, but we definitely know about the electromagnetics, the Maxwell's equation. It's just the backbone of, I should say, all of the aspirants who have taken the engineering courses. At least you might have at least you might have dealt with it in your 10 plus 2 level or 10 plus 1 level even. So that is the first week which we will be dealing about. Then the second week we will follow is the light matter interaction. So this particular part will be totally new to you guys if you don't have any, I should say, knowledge about how the light interacts with the matter. So let's say, for example, you have a in the first part, you will be mostly, let's say, dealing with the basics of electromagnetism. This is the basics of electromagnetism, electromagnetic waves, how they behave. Let's say you will talk about refractive index. You will talk about a new thing that you might not have maybe studied in your undergraduate courses or your basic level courses, is that refractive index is basically a complex quantity. That means it is no longer a real quantity what you were being taught in the earlier classes. We knew that if this is, let's say, for example, N1, this is N2, for example, this is air and this is water. So we were definitely taught that this refractive index is 1, this particular refractive index is, let's say, 1.5 approximately. So, but these are like real numbers we were being taught earlier. But later on, when you just advance in the optics course or the photonics course, you come to know that this can be even negative. It can be positive, it can be a complex quantity, it can be imaginary. And what do those quantities represent physically? Mathematically, you can just relate it with these are just imaginary quantities, and you can solve the equations. You can solve the Maxwell's equation. You can solve any of the differential equation with the imaginary term. But what are the physical interpretations of that particular imaginary thing in the refractive index? So that's what basically is going to be covered in the week one. And definitely, professor has tried his best to cover those particular concepts in the week one. We will try to just brush up here in this particular session. In the week two, we will be dealing with mostly the light matter interaction. So what is this light matter interaction? Is basically you are going to see the fundamental reason what happens at the atomic scale, but this is just the classical interpretation, or what you call as semi-classical. Semi-classical. Semi-classical means that you are treating the photons as an electromagnetic waves, but you are treating the entire material as a group of as atoms. So that is what basically semi-classical means. Let's say, for example, if we give you an example, what basically the week second will deal. So the light matter interaction part, which is basically light matter interaction part. So here you will be, I should say, talking about you will be you will come to know what happens when, for example, if this is a material. Let's say, for example, this silicon, and you have a crystalline silicon, you have the well arrangement of atoms inside the silicon. And if you shine a light, for example, you have some laser or you have certain light source, you shine it on the silicon. So what happens in the at the atomic scale? So what happens is basically that is basically covered in this light matter interaction part. And why I say this is semi-classical, the reason is, for example, if you have light incoming and if you have material, you have atoms inside it. If you treat this light as an electromagnetic wave and you treat these atoms as the atoms as such, then this is basically something called a semi-classical model or semi-classical theory. But if you have, let's say, a light, and if you deal with atoms as such, but if you deal with light as photons, and if you now compute all of the things in terms of how the photon interacts with the atom, single atoms, that case is basically, let's say, for example, even this is purely, I should say, semi-classical. Now, what is purely quantum mechanical case? If you have a quantum case, in that case, you have the incoming photons, which is the quantum object, and you deal with the atoms and the electrons on it in terms of the quantum mechanical entities. Now you no longer are treating it as a classical problem. You solve everything in terms of quantum mechanics. Here you have to see how the single photon interacts with the electron and what happens in that interaction. So it's like an electron photon interaction. So that will be a purely quantum mechanical picture. And I guess that is not the thing you will be dealing here, except by the end of this course. Mostly you will be taught about how a classical wave interacts with the atoms and the electrons, obviously. So it's just like an electromagnetic wave is coming, and what it does to, let's say, for example, electrons. maybe it will oscillate it back and forth, maybe it will do certain other things. So that is the fundamental thing you are going to study in the light matter interaction. And the basis of it is definitely it the base of everything is whatever you have studied in your 10+1 and 10+2 levels. So if you know the harmonic oscillators, you know about the how the simple pendulum behaves with certain spring constant k and certain mass attached. If you know this particular system very well, if you know the mathematics of it, then the semi-classical model of the light matter interaction should be a cakewalk for you. So it's just about how you understand the classical oscillators in terms of the mathematics. So that is the week two. And the week three, we will be talking about mainly plasmonics. It is a different thing altogether. We will be talking about size-dependent absorption and scattering. What happens if you go on reducing the size of, let's say for example you have some structure and you have a huge size which is much greater than, let's say, wavelength, and if you go on reducing this particular size and make it of the order of wavelength or few wavelengths, so how the light is going to behave in that particular structure, that is basically going to be dealt in this week 3. It's basically plasmonics is basically, it's just like collective excitation of the electrons. Okay, so if you know about, let's say, for example, this is something called as plasmons. For example, if you have a metal, you know in metal there are free electrons. So you have free electrons on the surface. There are a lot of free electrons. That's why it's highly conducting. But what happens if you just shine a light over the metal? It turns out that at certain frequency, it's just like it's just like the resonance phenomena you have studied. It's just like that light resonates with the electrons, free electrons present over the metal. Okay, so at certain frequency, what happens is that all of these electrons in the metal, these electrons, they just couple to the light in such a way that it behaves like a single wave is getting modulated inside the metal. It behaves like a wave in the metal. Okay, so that is called as collective excitation of electrons. So that is basically called as plasma or plasmons, whatever you call it. Okay, so these are just fancy names you don't need to worry about. So if you talk about, let's say, for example, starting from the earlier, what happened basically, we know about fermions, we know about bosons. So what is included in the fermions? Let's say, for example, electron is a fermion. It's just the particles having the half integer spin. You don't need to worry about these things. If you know that is fine. But if you don't know fermion, if you don't know boson, that's absolutely fine. But at least you know about electron. You know about photon. Photon is a boson. And let's say, for example, you have photon, you have phonon, you have maybe other bosons or other. These are something called as quasi particles. So why are these called as quasi particles? Because they are not real particles. They are just something with which you are interacting with two systems. Okay. For example, electron, for example, if you give the energy to the electron in the semiconductors, we have basically energy levels. You might be knowing about it. And if you have the valence band, you have the conduction band. If you give some energy to the electrons, it might go to the higher energy level. Now the electron is here. Now the electron comes back to its natural ground state energy, but in the process it emits a photon. So while emitting this photon, what does this photon indicate is that it is something which is basically given out. It's just like an interacting particle or interaction particle, which is basically which helps to, I should say, maintain the interaction between the two systems. It's just like field. If you have, for example, let me give you an example. If you have, for example, electron going in this direction, and let's say, for example, let's say, for example, there's an atom, there is something hit the electron, and electron now goes in this direction. The extra energy which is released in this process will be given to a system in the form of, let's say, a field. And this particular field, if you, I should say, quantize, I should not use these terms because these are like fancy terms. If you quantize the field is a continuous thing, but if you quantize it or discretize it, you get a quasi particle. You get a quasi particle. Okay, that quasi particle is most of the times bosons. It can be a photon, it can be a phonon. Okay, so that is basically the concept of quasi particle. In the final session of this, basically, if you talk about here, week 11, you are going to study about this canonical quantization. That if you have a continuous, let's say, for example, if you have an electromagnetic wave like this, for example, this is the electric field, so this is the magnetic field, this is the magnetic field, this is the magnetic field. Okay, so this is the H field, and this is the direction of the propagation of the wave. So in the what happens is that if you just quantize this thing, how do you quantize? That's a different story. It's not just like you have a continuous signal and you take some discretized units and you get discretized form of the wave. It's not as simple as that. Maybe you can understand it in that fashion, but it's not what exactly quantization means. If you quantize it, you get a particle picture, which is basically a photon. So this is something called as second quantization. Second quantization. Okay, the similar thing happens if you, let's say, for example, deal with, for example, any of the field, any of the continuous field. Okay, you have the electromagnetic field, which basically transmits electromagnetic energy. You have, let's say, for example, acoustic field. Acoustic field is like the acoustic wave. For example, I'm talking right now, so I am just vibrating the atoms in the air. Okay, but it's a continuous the air is filled with molecules, it's filled with atoms, so it's a continuous, I should say, medium filled with certain atoms. Okay, now for example, if this is the air I'm talking in, and you are hitting it with the sound wave, so the atoms in it, let's say for example, these are the atoms, so the atoms in it are going to compress and there'll be rarefactions. So you know how the sound wave flows. These are just the longitudinal sound waves are just the compression and rarefactions. So some of the atoms, let's say for example, at this position will come closer. Some of the atoms here will go farther. And similarly, so these atoms will come closer, these atoms will go farther. As a result, the acoustic wave will flow in this direction. So that's why it's a longitudinal wave. It's a longitudinal wave. Okay, because the direction, the motion of the oscillation is in the same direction as that of the propagation. So that is the longitudinal wave. But it turns out this is the acoustic wave I'm right now talking about, and I am right now emitting a lot of acoustic waves. Okay. Now what happens? It turns out if you have this wave, which is a continuous wave, now you can just represent it in the form of a wave. Let's say for example like this, where these are the regions where the atoms are very closer, these are the regions where atoms are farther, closer, farther. Now this wave, which is a continuous wave, it can be quantized using something called a second quantization. I said you will talk about it in the week 11 or week 10, I guess. If you quantize it using quantum mechanical principles, you get a quasi particle, and that quasi particle is basically phonon. Okay, so that means if you want to arrive at that particular quantum mechanical entity, which is basically governing the flow of the energy in the medium, you need to understand the quantum mechanics, how you go from a continuous picture to a quantum mechanical picture. So that is the understanding, or that's the notion of how you arrive at a photon picture, even how you arrive at a phonon picture. And there are a lot of other ONs, the names ending with ONs. Just like I said, there is photon, there is phonon, there is maybe plasmon, there is magnon, there is what else is there? Polariton, and there is maybe polaron, all other sorts of stuff. Maybe you can just Google and you will find the other quasi particles there. But what are these? Basically, are just the notion that these are something like I should say continuous fields. These are fields which are basically propagating energies between two interacting particles, actual particles. Let's say when I talk about particles, I talk about something like electrons, maybe protons, neutrons. These are the actual particles. But these things are the fields, like these. Okay. And that is the similar notion in, let's say, for example, if you talk about magnon. What is a magnon? Maybe you might get worried about these names. These are just the fancy names, but these can be, I should say, the concept can be simplified in terms of the basic entities you know. Just like the photon, it's just like the quantized version of the electromagnetic wave. The phonon is the quantized version of the acoustic wave. And phonons are even present inside semiconductors because the atoms can vibrate inside the semiconductor. And if you just quantize that particular vibration, you get a phonon. Similarly, plasmon I talked about, if you have a continuous oscillations of the free electrons in a metal, now for that continuous free oscillations of the electrons can be quantized using second quantization and you get a plasmon. Similarly, magnons are just like if you have certain magnetic materials. For example, if you have certain magnetic materials, and let's say, for example, this is a ferromagnetic material, and the specific property about these materials is that they have certain domains where the spins are having certain alignment. So this is related to the spins of the electron. So spin can be either upspin or it can be downspin for the electrons. So what is that now spin? We don't want to go into the philosophical or the theoretical aspect of it. We know about the spin of the electron. So there are certain domains inside this ferromagnetic system wherein, let's say, for example, all of the spins are upspin. Okay. Now, for example, if something happens that if you have, for example, if you give any of the disturbance to the medium, to the ferromagnetic material, and let's say, for example, the spins become like this, like these, just like, for example, okay, let me draw it like this. Okay. Yeah, for example, you did something to the system, any disturbance, and the spins oriented something like this. This spin orients in the up direction, then there is a turning of the spin. Okay, it just rotates in the entire domain. Now, what happens is that you can treat this particular system of spins as a wave, just like this. Okay, as a wave. And now, if you quantize this wave using the second quantization I talked about, what it is mathematically, you will talk about. We will deal with it in the upcoming weeks. If you quantize this wave, spin wave, you get a quasi-particle which is magnon. So then we treat it as if there is some I should say hypothetical subatomic I should say hypothetical quasi-particle which is basically moving from this end to this end, and that that quasi-particle is basically the magnon. Otherwise, it's just a field which is basically continuous field. Okay. Similarly, there are all sorts of other fields, polariton, polarons. Maybe you can just learn about them. And there is also something like the electron, photon, and phonon. They can couple with each other. Okay. When I say couple, I mean to say that, for example, if you have a system where there is an atom, if you have, for example, the electrons here, these are the electrons, then you know that atoms can vibrate. For example, something happens that this atom comes closer, these atoms come closer to each other. Then what is going to happen to the energies of the electron? They are going to change, obviously, because the electron's energy also depends upon how closer the atoms are or how farther the atoms are. Okay, and where does this picture come from? It comes from your basic semiconductor physics, basic semiconductor physics. In the basic semiconductor physics, we are always taught about something called crystalline systems, where there is a long range order of the atoms. Let's say, for example, you have some semiconducting material, then the atoms are just like this, arranged in a well ordered fashion. Okay. Now, if you just take one atom, you know that atom has a positive nucleus. It's surrounded by the electrons, classically. Okay. Now, how do you treat it electrostatically? Electrostatically, you have a positive charge and you have an electron. And you know that how you draw the potential energy profile for such a system. If you have a positive charge and if you have an electron coming towards it, your potential energy profile will look something like this. So this is the potential energy as a function of, let's say, x, and this is x. So it will look something like this. Okay. So this is the potential energy profile of a single atom. Let's consider, let's say, for example, if you have a hydrogen atom, how does the potential energy profile look like if you have a single positive charge and if you have an electron coming from the infinity, that is as per the definition of the potential energy, you will have a potential energy profile something like this. Okay, now that basically is extended to multiple atoms. Now you don't have a single atom, you have multiple atoms. You have atom here, you have atom here, another atom. So you will be having another potential energy profile, another potential energy profile, another potential energy profile, so on and so forth. So this goes on in a three-dimensional fashion. I'm showing it just in a 1D chain. Okay. Now these potential energy profiles, it turns out you have certain overlapping regions, which are basically these regions, these regions. Okay. You have certain overlapping regions. Let me draw it. These overlapping regions in the potential energy profile, and they go away, and you have the final potential energy profile, which looks something like this. So this is the chain of atoms, so it's continuous. So you have the final potential energy profile, which looks something like this. A common figure to start with in the semiconductor physics. And if you have now an electron here, now what is going to happen to that electron? That is basically what we study in semiconductor physics. Now the electron, for example, whenever you have this now potential energy profiles, you have certain energy levels inside it where the electron can reside. This is the similar picture of let's say if you have a hydrogen atom and you have orbits. That is basically comes from this. That basically comes from this picture. Just drawing the I should say the potential energy profile. Now what happens basically in semiconductor physics? What we do is that if we talk about let me just drop this. Let me just drop this. Where's it going back? Okay. So if we talk this potential energy profile, what happens basically? How do we get energy levels out of potential profile now? That means the orbits of where the electrons are going to stay. These are just potential energy profiles. Okay. Now what we do is that for that we basically solve Schrodinger equation. And all of you know about Schrodinger equation. This is the Schrodinger equation, let's say in one dimension, plus some potential energy wave function equals to E psi. This is the time independent Schrodinger equation. What do we need? Just don't worry about the fancy name, the Schrodinger equation. It's just a partial differential equation. And what do you need to solve it is this potential. You don't know this thing. If you know about this potential as well as the energy, you can just put it inside and you solve the differential equation for the psi, which is the wave function of the electron. Now this V, which is the potential, you get it from here because you know these are the potential energy profiles. And for an electron, let's say the the potential energy is basically Q times the potential. This is the electronic charge times the potential. Okay, don't get confused with it. And what you do is that if you have these potential energy profiles for the electron in an atom, you approximate them as, let's say, for example, square potentials. For example, because you don't want to deal with these curves. These are mathematically difficult to solve. These you can solve it numerically, obviously, but there are challenges to solve these particular curvatures, okay, because these are just like x square terms. Now what you do is that you simplify this particular potential profile and you treat it as if these are just like wells, square rectangular potential wells. Okay, you approximate it, and now you have the rectangular potential well, and you know that the distance between the two atoms is just like you represent, let's say for example a, maybe let's call it lattice constant. For example, if this point is 0, if this point is A, let's call this point as B, then this particular arrangement is going to repeat with this particular period. Okay, with this particular period, A plus B. So there will be repetition of it. Now what you do, you take one well, you take one of the wells, you take one of the wells, and you consider the electron to be here, and you solve the Schrodinger equation for it. Okay, you solve the Schrodinger equation for it, putting the V value as certain some V constant value. Okay, now when you solve the Schrodinger equation, what do you get? You get you get interesting things. You get a wave function of the electrons. You can as well get the energy because this is just like an eigenvalue problem. It is just like an eigenvalue problem, just like this, where this h is basically the Hamiltonian. It is the E minus h bar square over 2m dou square by dou x square plus the potential. This is the entire Hamiltonian, which is the kinetic energy part and the potential energy part. Okay, the wave function psi is a function. This E energy is basically the eigenvalue. It's the eigenvalue. It's like most of the times a real number. It gives you the energy value inside the system. And this particular psi is basically again the I should say a wave function. It's a function. So you solve this eigenvalue problem and you get the energy. You get energy in terms of certain I should say certain, for example, if you want to, for example, solve this particular equation, you solve this equation, you get wave function first as a function of x because it's a time independent Schrodinger equation. Well, now what you do once you get the wave function, you don't exactly solve it like this way. I'm just trying to give you a brief overview. In order to solve this differential equation, you need first of all boundary conditions. You need initial condition, not initial conditions here, but you need the boundary conditions. The boundary conditions is that what happens to the electron at this particular point. What happens to the electron at this particular point? So those are basically the boundary conditions. And you might be, so those of you who have studied about these systems know about something called as Bloch's theorem. So Bloch's theorem is quite a cool trick basically. If you have a repetitive arrangement of atoms, then if you have the wave function of the electron in this particular well, then you would be knowing that what is the wave function of the electron at this particular point. That means if you know what is happening to the electron here, you know what is happening to the electron in the other well. So that is basically what Bloch's function or Bloch's theorem tells us about. It's a very cool thing. Maybe you might have studied about it. So it's just like because the entire thing is repetitive. So if you can solve for this particular system, you can easily tell what is happening to the electron here, 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 and other things. Except there will be some phase term that comes because of e to the power some ik term. This is basically the phase term. That means if you have, let's say, for example, a wave function at some point, let's call it x, that will be equivalent to wave function at some point x plus, let's call it b. This point is b. It will be equal, but except that there will be some phase term associated with it. Okay, so that is basically the Bloch theorem. So when you solve it, you get finally the solution as the energy of the electrons in terms of something like Ka, which is basically this K, which is the wave vector of the electron. Because now you are treating the electrons as a wave inside these wells. You are no longer treating electrons as a particle. Because this Schrodinger equation, it's a wave equation. Okay, it's a wave equation. It's not a particle equation. So once you invoke the Schrodinger equation, you are going into the quantum mechanics of the electrons. Okay, once you solve this particular equation, you get energy versus the wave vector, energy versus k times the lattice constant. And what you get is that you get some curves like this. Not like this exactly. Oh God. You get something like maybe let's initially it was like this. You get something like this, something like this. You get some curves like this, and most of the people really definitely are confused about what these curves basically indicate. So what these indicate is that these are just like the dispersion curves of the electrons. That means if you treat electrons as a wave, so what is going to basically happen is that there will be different values of the wave function, which is basically a wave, just like for example, if you have a electron's wave function, let's represent it as, for example, some sine wave, sine of kx with certain some constant here. It doesn't matter. So what happens basically is that now you're treating the electrons as a wave, so you have to deal with dispersion of those waves, okay, inside the lattice. And why I bought this particular concept here is because that is the same thing what happens with the electromagnetic waves. So what does basically dispersion mean? It is just like if you have a system, if you have atoms, if you have atoms, and if you just shine some waves over it, any wave, like let's for example, you shine certain electrons over it on the all of the sides. What you will see is that not all of the energies of the electrons are going to be accepted. Okay, so that is basically a system dependent thing. If you change the lattice altogether, electrons' energy levels will altogether change. That means there will be a change in this particular dispersion figure of the electrons. I'm talking about the electrons. So that is basically the notion of the dispersion. That means giving, if you have certain system, you give in certain waves coming in all together in the system. The system will not accept all of the waves. It will have certain values where the electron's energy is not acceptable, and that those are these values, which is basically called the band gap. That is basically the notion of the band gap. It basically comes from the wave picture now. And there will be certain values which will be acceptable, which are shown as these black curves, acceptable values of the electrons. That happens similar in case of if you have a if you have an electromagnetic wave coming in. For example, if you have an atom, if you have atoms, and if you shine electromagnetic wave onto this system, the system is not going to accept all of the frequencies. Frequency means energy, okay, because E is h times nu. So it's not going to accept all of the frequencies. There will be certain frequencies which won't be accepted by this particular system. Okay, because of this particular arrangement. I'm just talking about the arrangement. Okay, what happens at a deeper level is a different story. So that basically gives rise to certain acceptable values and certain unacceptable values. In terms of the electrons, these are called as band gaps. Okay, there is another thing which is something called as photonic band gap. Photonic band gap. Photonic band gap is if you shine the electromagnetic wave or the photons over this particular system, it's not going to accept all of the frequencies. Some of the frequencies will be rejected. That will give rise to a gap, though that gap will represent that this particular electromagnetic wave is not being accepted by the system. Okay, that is basically called as photonic band gap. This is the electronic band gap. Electronic band gap. Okay, too much about it. Now, what is basically happening is that if you now talk about the Maxwell's equation, directly from what a professor might have taught about in the course, you know about the basic Maxwell's equation, the four Maxwell's equation, which represents the Gauss's law, the Faraday's law, Ampere's circuital law. Okay, you can basically combine these two Maxwell's equation into a single equation in terms of the time dependent part as well as the spatial part. What you basically have to do is just have to apply curl. If you apply curl on both of the sides, just like this, curl of B, and if you put del cross B as this particular thing, you put it here. This is some particular identity. I guess this is like minus del square E. This is an identity. This particular part comes out to be equivalent to 0. This is basically the spatial gradient of this spatial the gradient of this particular electric field. And what basically happens is that once you solve it, you arrive at this particular equation. Just a simple two-step problem. This equation is a wave equation. You have been dealing with wave equations from quite a from the starting. It's just like you have something like, for example, if you have a function f, if you have a function f, you can write a wave equation like d square f over dx square in terms of one dimension to be equivalent to some velocity of that particular wave times that function's temporal variance, temporal, I should say, change, but it's like a double differential. So this is the wave equation, which directly comes from the Maxwell's equation. Now you know that how do you solve this particular wave equation? You just assume certain solutions. you assume some, let's say for example, e to the power some exponential of I kr times omega t as the solution, and you put back into this equation and you solve for it, and you get the electric field and the magnetic field. And once you get the electric fields and the magnetic fields, they are basically the oscillating parts, and they represent the electric component and the magnetic field component of the electromagnetic wave propagating in the free space. We are right now talking about the free space. So if you talk about these electromagnetic waves, so these are the electromagnetic waves. This is the H field, and the underlined one is the H field, and this is the electric field. So these are mutually perpendicular to each other, and they are perpendicular to the direction of the propagation, which is z direction. So E is perpendicular to H, and it's perpendicular. Both of them are perpendicular to the direction of propagation, which is z. So that's why these are called as transverse electromagnetic waves. Transverse means they are perpendicular to each other, and they are perpendicular to the direction of the propagation of the wave. Later on, you will see in this course there are something called as transverse electric, transverse magnetic. These are again understood by the same analogy. In the transverse electric component, the electric field is perpendicular to the direction of propagation, and the magnetic field component is in the same direction. This is transverse electric. The transverse magnetic is the magnetic field component is perpendicular to the direction of propagation, and the electric field component is parallel to that of the direction of propagation. So these are transverse electric and transverse magnetic modes. So these modes are nothing, these are just the solutions of Maxwell equation in different systems. Just like if you have this Maxwell's equation, this differential equation, you solve it for a free space, you solved it for a free space where there are no charges, there are no free charges as such. Okay, there are no polarizations coming into picture. When you solve it for the free space, you get these plane wave solutions as a transverse electromagnetic wave. Okay, but if you consider this same Maxwell equation, for example, Maxwell equation, let's say for example, in a system called as waveguide. For example, waveguide is something, it's just like a something which guides the wave. That is as simple as that. If you, for example, consider waveguide, for example, you have a, let's consider this as some material, let's say silicon, and this is like a silicon bar. Let's call it, this is a substrate. And if you have certain other material over here, you don't know this material, let's call it material A. What will happen is that if you now somehow electromagnetic wave comes in, hits this particular side, okay, you will see that most of the electromagnetic wave will go through this particular system, but it won't go through as the wave it was in free space. Let's say, for example, in free space, it was transverse electromagnetic wave coming in. But once it goes into the system, it has a different acceptable solution coming from the Maxwell's equation. And that is not necessarily a TEM mode. Okay, that can be a transverse electric mode, that can be a transverse magnetic mode. Okay, so those modes are basically now the solutions of Maxwell's equation in this particular system. That is the simplest notion of what the mode is. So now the electromagnetic wave will get transmitted in the form of certain mode profiles. It can be transverse electric, it can be transverse magnetic. Most of the times these waveguides don't support transverse electromagnetic waves. If you want to know the reason, you can just look for it, why that is not the case. It just depends upon the boundary conditions. Okay, so that is the notion of how what you are also going to study in this particular course, how these waves, electromagnetic waves, propagate in a nano structures. Okay, let's say for example you have certain structures. Let's say for example this is a this is, let's say, material A, and if you have certain nanostructures, circular nanostructures present in between, which are very small, of the order of nanometers, nanoscale size. And if you irradiated this certain electromagnetic wave, you're going to see that electromagnetic wave is going to propagate in a different way altogether. For example, if here it was transverse electromagnetic, once it is going to hit the system, it's going to behave differently because of these nano or because of these different materials. Why does that happen is because now it has encountered a different refractive index altogether. Okay, it is just like if you have, for example, let's say uh, if you consider, for example, electron, if this is a well, let's call it it's something called as quantum well. It is the same well I talked about here, the atoms, the atomic potential energy profile. This got converted to square potential wells. If you talk about one of the wells, if you solve the Schrodinger equation for it, you get the energy levels as discretized. Okay, you get discrete energy values, E1, E2, E3, so on. So this is E1, E2, E3. Okay, so what are these energy values for? These are for electrons. That means, let's say, for example, if you have earlier a free electron can have a continuous values of energies. And for that, the energy is basically h bar square k square divided by 2 This is just like, I should say, energy of a free electron propagating in a, let's say, free space. Okay, it has a continuous values of energies. If you draw E versus K, the K is the wave vector, you have a parabolic relationship. Okay, and it can assume all of these values. The electron can have this value, any value falling on this particular parabola can be taken by the electron, free electron. But if you move this free electron in a confined structure, let's say an atom, because of confinement, when you solve the Schrodinger equation, it gives you the solution with discretized energies. The energy no longer is continuous now. Earlier you used to have a continuous energy, now you have a discretized energies. Okay, this particular plot is E versus X. This is a space plot. If you draw it in terms of the E versus K, you have energy levels like this. And each value is like, it's now a discretized value. Okay, so each value is now a discretized value. And also the band gap opens up because now you have put the electron in some system with many number of atoms. The band gap, the reason for the band gap opening is the same, the dispersion or the electron as a wave, as a wave, some of the values are acceptable by the system and some of the frequency values or the energy values are unacceptable by the system. It opens up a band gap. And now when you solve the Schrodinger equation, you get energy levels, and these are energy levels for the electrons. And let's say, for example, for equals to 1, the the wave function for the that is the psi 1, it looks something like square root of 2 by L sine of maybe kx. Okay, this is the solution of the Schrodinger equation, this thing. Minus h bar square divided by 2m d square psi over dx square plus some potential times psi equals to E psi. So you solve it simply by just rearranging the terms d square psi over dx square plus, you can write it as not plus, you can write minus 2m over h bar square E minus v times psi equals to 0. Now you have this differential equation. Okay, where this can be written as d square psi over dx square minus k square times psi equals to 0, where k square is twice m over h bar square E minus v. This is the k wave vector we are talking about. And you have the differential equation d square psi over dx square minus k square psi equals to 0. This differential equation, you might have solved thousands of such differential equations. When you solve, you get a solution as sine or you get a solution as cosine. Now it depends upon the boundary conditions, what are the acceptable solutions. Okay, the acceptable solutions depend upon, because the electron's wave function should terminate at these ends, because electron is not allowed to go outside this confined well. So you apply the boundary conditions accordingly. Okay, when you apply those boundary conditions, you get you get the solution in E equals to 1, which looks something like this. Okay, which is basically psi 1. So this K here is basically the wave vector. And when you solve when you solve this particular problem, you will see that this wave vector is quantized in terms of n pi over, let's say, dimensions L. This is the L. L is the total width of the quantum well. Okay, so n is basically the integer. It is just like the if you go on, for example, increasing the value of n, you go to higher and higher energy levels. For example, for this is n equals to 1, n equals to 2, n equals to 3. Now, why I'm showing this problem is because it has interesting aspects or interesting resemblance with what happens with the electromagnetic waves. Now, when you have the wave function, now you have this particular wave function. If you draw it for the e equals to 1, it looks something like this. This is basically a infinite potential. Well, infinite means this is way too deeper than this particular level. So it's a the potential inside is zero, but the well is very deeper. Okay, in terms of the external this particular reference value. Okay, that is basically the notion of infinite potential well. So the infinite well is just like the electron is just trapped there; it cannot go outside. That is the notion of the infinite potential well. When you solve it, you get the first solution as something which looks something like this. And you get the second solution, something looks like this. You get the third solution, which looks something like this. So these are just the solutions of the Schrodinger equation. Now, if you talk about this was for the infinite well problem. If you have a finite well, you solve the same Schrodinger equation with appropriate boundary conditions. You get the solution as something which looks like this. It is similar, except that there is one important difference. And that difference is basically this particular decaying part. This particular decaying part. That means if this is the well, quantum well of length L, you don't, I should say, consider that electron will be present outside the well because it's just like a trapped system. But what Schrodinger equation tells you, the solution of Schrodinger equation tells you that there will be some e to the power some minus alpha x terms on both of these sides, which is very strange because that means the electron's wave function was just like this. Earlier it was just like this one. That means the electron was completely inside the well. The wave function basically psi of x shows you it gives you the basically the probability. If you mod square it, this is basically the probability density function. Okay, it tells you what is the probability of finding the electrons. So earlier it was fully inside the well, but now because you are considering the finite potential, what has happened is that you have these leaking parts of the wave function. These are leaking, and these are basically something called as evanescent modes. Let's call it evanescent decaying part. These are these represent that the probability wave function of an electron is leaking outside the well. That means there is some finite probability of electron being found outside the well. Okay, most of it is inside the well, but at certain instant, if you look, you can find the electron outside the well. So that is basically the part what is basically something called as quantum tunneling. You might have heard about. This is basically part of quantum tunneling. I'm talking about electrons purely here. I'm not going into photons yet or the electromagnetic waves. So what happens now? Here you had a electron in a potential well, and why how this potential well is formed is because of atoms. Repetitive arrangement of atoms. It forms the potential wells. Not like this. The potential is down here, and it looks like this. This is the potential wells. And if you solve the Schrodinger equation for it, you do the same problem. You get those decaying waves. And now, what happens if you have this was purely because this was because purely because of potential energy reasons, potential energy profile. Now, it turns out if you have a similar system wherein you have a variation in the refractive index instead of a potential energy. Let's say, for example, you have, let me give you example of, let's say, for example, this is some system, this is some substrate, and Let's, for example, there is another material present over here with a different refractive index. Let's say N2, this is N1. Let's say N2 is greater than N1. And if you draw the refractive index as a function of X, it will look something like this. This will be the refractive index profile, okay, for the with respect to the X, spatial refractive index profile. It will not be exactly square, it will be somewhat like this, but let's consider it as a square. Now, what happens? You have to do the same exercise now. You have to consider a photon or the electromagnetic wave. Let's talk about electromagnetic wave here right now. And you have to solve a wave equation. Which wave equation? You don't solve the Schrodinger wave equation, you solve the Maxwell's wave equation because the electromagnetic wave is a classical thing. You solve the Maxwell's wave equation again, Maxwell's equation. When you solve the Maxwell's equation, you get the solutions. You get the solution as sine or cosine, depending upon the boundary conditions you use. It turns out if you do this problem, if you solve it, if you now solve it using the particular boundary conditions, you arrive at solutions which can be either transverse electric or transverse magnetic. And the profile or the mode solution will look exactly similar. If you have, for example, if you talk about TE10 mode, these are just like indexes. Don't worry about these. But what I'm trying to say is that you will get a similar, let's say for example, a profile of the electromagnetic wave propagating through this system. It will look like something like this. This will be the TE mode, first TE mode. It's just like the it's just like this. The first solution of the wave function in n equals to 1. In n equals to 1. Similarly, if you go on to higher modes, you can have a solution of a Maxwell equation which may look something like this, bimodal. Similarly, if you go on higher modes of the Maxwell's equation, you can have a solution which may look something like this. Okay, so there is a resemblance because the governing equations are similar. These are the partial differential equations you are trying to solve. But what I'm trying to say here is that here you have the electromagnetic wave moving just like a Gaussian packet inside this entire waveguide, just like in the form of a transverse electric mode. So that is how it propagates. It propagates just like these in this direction. So if you have an electromagnetic wave coming in, because of Maxwell's equation now, it has a different acceptable solution inside the system. You solve the Maxwell equation considering the boundary condition, you get a TE mode which can propagate inside this waveguide in this particular direction. This is for, let's say, for example, first mode, first TE mode. Similarly, if you go into higher modes, you can, let's say, for example, say this is second mode, higher mode, this is third mode. And you see that there is weird resemblance of this with that of the electrons in a potential well. Electrons in a potential well. It also has a similar solution, except that the here it represents the psi, which is the wave function of electron, which gives the probability of finding an electron. But here, the solution of the Maxwell's wave equation gives you the electric field amplitude. Electric field amplitude. That means E. Okay, so this is basically the electric field amplitude propagating through the waveguide. It's not the probability of finding the photon. Don't get confused with it because you're solving Maxwell's wave equation. And the wave equation is solved for the electric field or the magnetic field. But for the electrons, it is the probability. But you see that the solutions have a similarity. Now the interesting part. You had the refractive index gradient. So this is N1 refractive index, this is N1, this is N2, and N2 is greater than N1. So what happened is that when you solve the Maxwell's equation for this particular part, you have the mode propagating like this in this direction. Okay, so now interesting part is that there is also these leaking parts. Okay, so this leaking part is it's leaking from this particular higher refractive index towards this lower refractive index part. So this is the evanescent part also here. Evanescent part. So it's just like the electric field component is not exactly terminating at at this edge. It's not terminating at these edges. But there is a finite chance that this wave, electromagnetic wave, can leak from this particular waveguide and go into the surroundings. Although the leaking part is very small, but it is always there. Okay, this is the evanescent part, or you can think is like a I should say tunneling of the electromagnetic wave. But this is a very classical phenomena here. But here, in terms of electrons, this tunneling is purely a quantum phenomena. It's a quantum phenomena. So you see where the analogy is and where you can basically correlate these two things. Because these are similar because the nature of the equations are similar. You are solving the partial differential equations. You are getting similar set of solutions. But the Schrodinger equation gives you probability density, probability distribution function, which is the psi or mod square psi. And this particular thing gives you the electromagnetic field, electric field amplitude. So that is the notion of this particular thing, where you can basically understand the evanescent part and the I should say the tunneling part in the electrons and the evanescent part in the electromagnetic waves. Now, if you, let's say, for example, bring some other structure, if you bring that very close to this particular evanescent part, if you have another waveguide here with, let's say, for example, another refractive index of N2, what can happen is that this decaying part, evanescent part, can now propagate in this waveguide in this direction. Earlier you had a very small leaking part, but if you bring it another waveguide very close to this particular leaking part, this is very small distance and you can compute it mathematically. What will happen is that this leaking part will become a propagating wave inside the waveguide. So it is just like if you have a for example, if you have let me give you an example in terms of electrons. Maybe you can relate it with that of the electrons. Let's say, for example, if you have some if you just deposit layer by layer certain materials, let's say, for example, uh, let's call it material A, material B, A, B, A, B, such that, for example, for material A, the band gap is greater, and for material B, the band gap is lower. So when you draw the band diagram for it, when you draw the band diagram for it, which is the energy versus the space, X, it will look like something like this. Okay, not I'm messing it. Oh, no. This will look something like this, so on and so forth. So what I'm basically drawing is this is the conduction band for material B, this is the conduction band for material A, this is the valence band for material which one is it? B. This is the valence band for material A. So these are just like different materials stacked on top of each other, layer by layer, with different band gaps. Okay, such that, for example, for the material B, the band gap is this. For the material A, the band gap is this. This is EGA and this is EGB. And you can clearly see that EGA is greater than EGB. That means if you have a band gap variation in the materials, it will give rise to potential energy profiles or the band diagram, which looks something like this. Now, what is going to happen? Now, you have a system like this now, a similar one which was made earlier when many number of atoms were closer together. That also gave rise to a similar kind of a potential wells. But here this is artificially made. This is artificial potential wells. These potential wells are already there no matter what you do, because these are because of atomic potential. This is because of difference in the band gaps. Okay, it comes in because of also because of potential energies, but this is mostly because of the difference in the band gaps. So you have these band diagram which looks something like this. So this is the conduction bands, these are the valence bands. Okay, now what is going to happen if you let's say, for example, if you solve the Schrodinger equation for one of the well, you know that there will be some discrete energy levels. This is for electrons, and this is the blue one is for the holes. So that if you have, for example, the electron will look like something like this, the holes wave function will look like something like this. So this is the electron, and the green one is the holes. And you see that there is a leaking part here, and it may so happen that if you, for example, if you make the layers very thin, that means if you reduce this particular thickness, if you reduce this thickness, and if you make it closer to this evanescent part, that means if you make a well something like this, such that the leaking part is going into this well. Okay, now it will again behave as a wave inside it. It will no longer be a propagating wave. No, sorry, it will no longer be an evanescent wave. It will behave as a propagating thing, or I should say, a quantized electron inside it. But what is basically weird about this particular phenomena is that there is some energy level acceptable inside the well, but outside the well, because this is outside the well, what is this? This is entirely a band gap of material, let's say material A. In the band gap, you know the electron cannot exist. But because of evanescent decaying part, the electron exists there for a time being, but it decays quickly. Where does it go? That's a different question. But you know where is the ambiguity is that this is the band gap of some material, and in the band gap, the electron is not supposed to be there, but it is coming in there because of the evanescent decaying part, because of the tunneling. Now, if you bring in this particular system closer to it by making the thickness, by making it thin, you can couple the evanescent decaying part into this, and now the electron will have its own energy level inside the system. Okay, that is similarly if you have, for example, if you have a if you have a potential energy barrier like this is the potential energy barrier. Potential energy barrier. That means if you have potential energy barrier, let's say for example, there is some negative charge. Negative charge is going to have a opposite, different potential energy profile. What does it mean is that if, for example, electron wants to come closer to the negative charge, it will face repulsion. So it will be difficult for the electron to come closer to this negative charge. So that is basically the potential energy profile shown for this. Okay. Similarly, for the positive, it was opposite. Electron wants to come to the positive. That means the potential profile looks like this. It is almost like attracting. But for the negative, it's repelling. There's a barrier because of this negative charge. So now, for example, electron here is in, let's say, for example, this is, let's say, for example, free space. This is some medium because of which there is some potential barrier present here, which is basically this particular barrier. It is the barrier for the electron. Now, in the free space, the electron behaves as a plane wave, just like the electromagnetic wave. Okay, it is just like an electromagnetic wave. It is, I mean, the solution is like plane wave, which is basically some sine kx, maybe where k is basically continuous. It's not discretized. Or you can write it rather e to the power some I omega t minus kx. This is the solution of the electrons in a free space when you solve for the free space. Okay, and when you solve it, you get a plane wave solution. Electrons behave just like a plane wave in a free space. But once it hits, this is the propagating plane wave in the free space. But once it hits the medium, a barrier, which is a potential barrier, what happens is at this particular point, this wave basically starts to decay inside it. And once it decays, if it has enough energy to get to the other side, or I should say, if it has enough remaining probability to get to the other side, it will appear as an oscillating part again, as a free wave. So this is here free space. This is again free space. It's just like electrons behaving like a free particle here. It can be a free space, it can be something like a metal where the electrons behave freely without any influence of the atoms, just like something called as free electron model. What happens because of that? Now what happens, the interesting part is that electron was behaving like a plane wave outside. Free electron, this is like a free electron. Free electron. Free electron is a better term than compared to that of free space. So this is like a free electron, let's say for example in a metal, free electron. It was behaving as a plane wave, but once it encountered some potential energy barrier, it will go on decaying inside it. What is decaying basically is this wave function. And if you square the wave function, you get the probability density, probability distribution of that particular electron. Okay, now the weird part is that electron was not supposed to be inside, but now because of evanescent part, because of this tunneling, because of decaying part, which looks something like e to the power minus alpha x, there is some finite probability of finding the electrons inside this particular uh, potential barrier. But outside it again behaves like a plane wave. Okay. Now, for example, if you do something, if you make this, let's say, for example, the thickness of this barrier was earlier T1. Now, if you make the barrier very thick, if you make it to T2, where T2 is much, much greater than T1, and if you see you have a free electron coming in, it starts to decay, it starts to decay completely inside, and you get nothing here. That is the, it's also a weird part, but it's also the essential part of quantum mechanics. It is just like electron already knows that I'm going to hit something which is very thick or which is very thin. The barrier I'm talking about. Because in this case, the electron tunneled and it appeared on the other side as a plane wave. But in this case, electron tunneled, but it just got vanished. You get nothing here on the other side. And it can be controlled depending upon the thickness of these barriers. And how do you control the thickness of these barriers? By depositing different layers of materials. Material A, material B with different band gaps, with different potential energy profiles. That is how you do it basically, how you tune how you control the quantum tunneling. And that is the similar notion with what happens with the light. This was for the electrons. This was for the wave function of the electrons. If you have a similar thing for the light, let's say you have a structure like this, where you have electromagnetic wave moving like this. Now, because you know whenever the electromagnetic wave is moving inside this waveguide, it will appear as some modes. Let's say these are TE modes, where you have a propagating part in this direction and you have these evanescent decaying part in this direction. Okay, now what is going to happen? Similar situation. If you bring something in very close to this particular waveguide or whatever the material is, if you bring something very close to it, you can utilize these evanescent waves and you can make them propagating. That is the weird part. They were the decaying parts, but you can make them propagating. These are just like the high frequency parts, but you can make them uh, you can make them propagate in a different structure altogether. Let's say, for example, if you let me just draw it like this. Let's say, for example, if you bring in let's say if you bring in a waveguide, something like a circular thing. A waveguide can be of any shape, just like a circular medium that supports the electromagnetic waves, certain modes, TE, TM. Okay, but if you bring in it very close to this particular rectangular waveguide, this is rectangular waveguide, this is circular waveguide. If you bring this waveguide very closer to the rectangular one, and now you solve the Maxwell's equation again, but where at this particular point, you will see that the decaying part comes into this circular waveguide, and now it starts to propagate inside the circular waveguide. And there, this is basically coupling of the evanescent evanescent wave into the circular waveguide. And that is what I mean to say that you can utilize these evanescent decaying modes once you bring in something very close to these particular modes, just like the electrons. If you make the potential barrier very thin, you can get electrons on the other side as a plane wave, just like a free electron. If the potential barrier is very thick, you will get nothing. Similarly, if the circular waveguide is very closer to this the electromagnetic wave evanescent part, you will get a propagating wave inside the circular waveguide. That is the and that is the basically comes from the acceptable solution of the Maxwell's equation. You have to solve the Maxwell's equation again at this particular point. and you will see you get certain acceptable modes in the circular waveguide. So this particular arrangement is something called as a ring resonator. Ring resonator. Those of you who are from the photonics background may not know about something about resonators, photonic resonators or optical resonators. But the phenomena is similar. The phenomena is similar. It is the same phenomena if you have, let's say for example, you have a prism. A classical example, we all know about these prisms, and you have, let's say for example, a light coming in, it undergoes bending, then there is another part here, it can go outside. So there is a bending at these particular parts. So if you have, for example, this is the incident wave, incident light coming in at the prism, and you have the refracted part inside, which is this part, and you have the reflected part again inside, and then you have again the refracted part which goes outside. And let's not consider the incident rays falling at a total internal reflection angle. Let's say some angle, some theta. Let's say, for example, this is some theta incident, and this is theta refracted. Similarly, this is for this particular bottom part. This is theta incident, and this is theta reflected, r dash. Let me write it r dash. What basically happens? This evanescent uh, concept, evanescent decay concept exactly applies here also. What happens basically, the electromagnetic wave comes, it hits. Now it undergoes bending. All of the things professor has covered. There is a change in the wavelength. The frequency remains constant because frequency is a concept coming from the source. Whatever the source is emitting this, the wavelength changes. There's a bending in the wave, electromagnetic wave, just like this. Okay, the wave vector slightly changes. What happens? Now at this particular part, this is, let's say for example, this is N glass, this is N air. At the interface between glass and air, this electromagnetic wave, which was earlier in a plane wave form, this is a plane wave. When it hits the glass air interface, there is some part which basically decays outside, and the other part basically reflects, and then it refracts here back. Some part of, obviously there will be some reflection here internally also. Let's neglect those things. But this is the exact scenario. And the point of concern here is about what happens at these particular points. So basically at this particular point, there is certain part of the electromagnetic wave which basically leaks into the air. Okay, that is basically, for example, the evanescent part. Okay, and this mostly happens, you might be knowing, this mostly happens at an angle if the angle is if you're talking about the total internal reflection happening inside it. So whatever is feeding in, it gets internally reflected and comes back on the other side. That is basically the concept of total internal reflection. Otherwise, the electromagnetic wave can come outside on this particular side also instead of this side. But we're talking about particularly here, let's say total internal reflection. Okay, just like if you have an optical fiber, and this is, let's say for example, cladding, there is internal another structure which is basically core. Optical fiber is also like a waveguide. So if you put the laser at some particular angle which is equivalent to the total internal reflection, total internal reflection of this particular light beam, it will undergo TIR inside, and you will see the light waves propagating inside the fiber. But what happens basically at these particular points, at this and this, all of these edges where there are two different refractive index, cladding and the core. Here also the wave starts to leak. Wave starts to leak. There is a leaking part, and this leaking part is becomes very dominant when you have a long distance optical fiber. They contribute to a lot of losses. Okay, that is the similar concept happens in prism. If you shine it at a total internal reflection, you will see that there's a evanescent part at this particular point, which is basically a leaking part. And the important thing to note here is that if you somehow bring another prism closer to it in the opposite orientation, you can see that this particular evanescent mode can basically couple to the another prism, and you will get a wave coming out from this. You will get a wave from this propagating wave, because now it has got the medium to propagate based on the obviously the wave vectors, or you have studied in the lectures. So that is basically the notion of where you can basically use evanescent modes, evanescent decay, or these tunneling parts of the electromagnetic wave. So these are all the examples which are basically real life examples where they are used, particularly let's say in case of optical fibers. You have a 10-kilometer optical fiber or 50-kilometer optical fibers. Then these evanescent decaying parts are always there, and they contribute to a lot of losses, a lot of power loss, because whatever you are feeding in gets lost, gets some of the part gets absorbed, some parts gets decayed to the surrounding medium as a form of evanescent decaying part, and it contributes to a, I should say, different phenomena. And these are the some of the application parts, and how you can correlate these particular things, how you can correlate the wave function of the electron, the electric field of the electron, because for understanding the wave function of electron, you have to solve the Schrodinger equation. For this, you have to solve the Maxwell's equation. But the governing equations are the same. They are the partial differential equations with the same set of solutions, similar mathematical solutions. That is the essential part of it. Now, that is it about this. And now we talk about, let's say for example, this part has been essentially covered. These are basically the plane waves propagating through certain structure. Let's say this is air, this is glass. Then you see that plane as the plane waves propagate. This is basically the, I should say, top view of the air glass slab. You see that the wavelength gets changed. Okay, but this is what happens at the oblique incidence. At the oblique incidence, where the incidence is at certain angle, you have to conserve the for example you have the incidence like this, then you can anytime divide, I should say, distribute into two components. One will be kx, one will be ky, and you can write it in terms of, let's say for example, this is angle theta. You can write it as kx sine theta. You can write it as ky cos theta. Okay, that means if you have an electromagnetic wave coming in at an angle, you can resolve it into two components, and then you have, as per the boundary condition, at this particular interface, this component and this component is going to be same, because they are parallel components. So the parallel components are going to be same, but the perpendicular components are not going to be same, equal, because at this point there is symmetry breaking. There are two different mediums altogether. Okay, so the parallel component will be same, equal. The perpendicular component will not be. These are just like the boundary conditions of the Maxwell's equation. So there are four boundary conditions basically. There are, there is electric field, there is magnetic field. There are two boundary conditions for the electric field, two boundary conditions for the magnetic field. One is the parallel component, another one is the perpendicular component. One is the parallel component, another one is the perpendicular component. So when you solve Maxwell's equation at any interface, let's say this, you have to always consider, let's say for example, this is theta, and let's say this is when you distribute it, let's say this is sine kx sine theta, this is ky sine cos theta. You have to always think about conserving these parallel and perpendicular components of the electric field. Just like here, I told you that inside inside the medium, the kx components, the parallel components will be same, but that's not the case with the perpendicular components. So that means we are talking about mostly about these electric field components here. Similarly, when you deal with the materials uh, let's say for example, higher permeability, magnetic permeability, there you deal with these magnetic field components as well, the parallel and the perpendicular component of the magnetic field. Okay, so that is basically the notion of the oblique and the normal incidence. Now, what happens basically if we jump into, let's say for example, what was covered in the week one, and if we try to solve the certain problems from the week one assignment problems. So first of all, we have the which of the following is, give me a moment. So first of all, we have to consider which of the following is true about the refractive index of an absorbing material when a broadband light is incident on it. There are quite a number of terms in it. First one is refractive index, another is absorbing material, another is broadband light. So broadband light is with broad spectrum. That means it is like a it's like a white light. It's like a white light consisting of many frequencies, starting from violet, indigo, so on up to red. So just like a broadband light. Absorbing material is something that has the capacity to absorb the electromagnetic wave. Now, what does it depend? Can all the materials absorb electromagnetic wave? The answer is no. It depends upon the refractive index. Refractive index basically can be computed even from permittivity. How well the medium can permit the electric field inside it. You represent with epsilon. And you know that refractive index, which is n, is approximately square root of epsilon. Talking about real part only. Okay, what does this permittivity depend upon and what does this refractive index depend upon? They depend upon band gap. So it depends entirely on the band gap of a system, whether it will be absorbing, whether it will be transmitting, whether it will be reflecting even. So there are three cases. Either it can be absorbing, either it can be reflecting, either it can be transmitting. And most of the times, all of the three things happen simultaneously. Okay, most of the times. For example, if you have some material and if you shine some light, let's say red light in this direction, there will be some absorption inside the material, but you will notice that some part of the red light will get transmitted, some part will get reflected. So this is the reflecting part, this is the transmitting part, and this part will be absorbed inside the material, and this absorption part basically comes because of the complex refractive index. Now the refractive index, we write it as n plus, let's say for example, I times k. So this particular part basically tells you how much is the absorption of the refractive index. How much is the absorption of the electromagnetic wave? Okay, it's the, I should say, decaying. How much is it decaying inside the medium? Just like if you have, for example, let me give you an example, then we can. If you have, for example, a glass slab, and if you have an electromagnetic coming, let's say, for example, this is water, and if you have an electromagnetic wave coming in, it will decay inside it, and then it can the amplitude will reduce, but it is going to, but this is basically propagating inside it also. So, but this is decay, but this is decaying amplitude. It is not the evanescent. Just make sure that you understand it. This is not the evanescent mode I'm talking about. I'm talking about electromagnetic wave coming in, and the amplitude is decaying, and then it's coming on the other side. Okay, these are propagating waves altogether. And similarly, if you have basically certain, for example, materials where you have the higher absorption coefficient. What is absorption coefficient? It is represented by some alpha, and it tells you, and the units of alpha are like 1 by meter. Okay, that means 1 by some unit of distance. That's why if you just inverse it, you get something called as penetration depth. This is called as penetration depth, which is given by 1 by alpha, and the units will be meters. It tells you how much the electromagnetic wave can penetrate inside the medium. That is the notion of absorption coefficient. So if you have a complex refractive index and the imaginary part of the refractive index is higher, then that particular medium will be highly absorbing. That means it will absorb a lot of electromagnetic wave in it, and you will get very little transmission. On the other hand, if the imaginary part is lower, then you can get a higher transmission through that particular medium and lower absorption. Okay, and this absorption is basically responsible for heating because of light. Let's say, for example, you have certain material, you shine some laser on it, it starts to heat up. Why does it start to heat up? Because corresponding to, let's say, for example, you are using wavelength, let's say, for example, 1000 nanometers. When you will see this material has a absorption coefficient of which is huge, corresponding to 1000 nanometers. That means it is absorbing the 1000 nanometer wavelength in itself. That is giving rise to heat. Because you will ask about the energy conservation. What happens to energy conservation? If the energy is coming in, it is being absorbed by the medium. Where is that energy going? It should have some other form of energy that is basically converted into heat. That is how it gives rise to the heating inside the medium because of the huge absorption coefficient. Now, on the other hand, if you have a different material and if you shine the laser, let's say for example the same 1000 nanometer laser, this was material A, let's say this is material B, and for the material B, let's say you have absorption coefficient for 1000 nanometer is very less. Let's say for example alpha is low. You will see there won't be much heating at this particular place. The heating in terms of the temperature rise will be very low, and the reason is because absorption coefficient is low. The reason is because it absorbs very less electromagnetic energy. Okay, so that is basically the notion of absorption coefficient. And the real part of this absorption coefficient tells us the propagating part. And this propagating part is basically propagating at a velocity which is basically something called as group velocity, which professor has definitely talked about. He has talked about the group velocity and the phase velocity. So when you have a electromagnetic wave, you draw its dispersion curve, omega versus k. It's flat in free space. But once it enters the medium, it attains some slope. The slope changes. And how much it changes depends upon the refractive index. Okay, and if you somehow compute this particular slope, you will get the d omega over dk basically gives you the group velocity. Okay, for the electromagnetic wave. And if you want to visualize it, there is a very good conceptual visualization on Wikipedia, and that basically shows what the group velocity and the phase velocity is. If you have a wave, and this concept is mostly applicable when you have many waves. It's not applicable to a wave of let's say single frequency. No, it has just a single. It can travel with a single velocity. But once you have multiple wavelengths, multiple frequencies, let's say something like this, and if you combine them, you may get a wave something like this, maybe. And then you talk about, for example, you may even get, for example, a wave something like this, okay, where you see that there is some slowly varying envelope part, which is this envelope, and there is some faster moving, which is carrier. Okay, in that case, you have to invoke this concept of, I should say, group velocity and the phase velocity. So the phase velocity is how faster the phase changes, and the group velocity is how faster basically the wave is traveling. That is the exact velocity with which the information travels, with which the wave is exactly traveling. So this is the actual velocity. That is why there is a notion that people are mostly confused about it because it needs a great set of visualization to understand group velocity and phase velocity. That's why you will see most of the times the phase velocity can be much greater than the speed of light. And people are like, what is happening? Nothing can move greater than the speed of light. But it is not the exact velocity of the wave. It is just the phases are moving at that particular velocity or changing. The exact information is traveling always at a group velocity, which is group velocity is always much less than the speed of the light. I should say approximately should say less or equal to speed of light, depending upon the medium, because the light slows down inside the medium. But the phase velocity can be much greater than the speed of light. That is the essential notion you need to understand. You can just search on Wikipedia about the group velocity and phase velocity, and there's a great and cool animation shown about these particular group velocity and the phase velocities. Because of the time restriction, I cannot go deeper into this. Otherwise, I just want to relate it with the electrons. Maybe next time we can do it. So the answer to this question is imaginary part determines the absorption. That's what we have talked about. The real part determines the phase velocity. That's not correct. The real part determines the group velocity, the propagating velocity of the electromagnetic wave. The refractive index is complex. That's absolutely correct. The real part determines group velocity. That's also correct. And this is the velocity with which the wave actually propagates. Okay. So this is the dissection of the question first. Moving on to question second. These are just like cakewalk questions, and you can easily solve them in your sleep even. You are given a momentum. You are to find the momentum of an electron, and you have to find the momentum of a photon, and compare it with the momentum of a photon. Let's say you are given a 2 electron volt electron. This is the energy of electron in electron volts, and you have to say, is it greater, is it less, or is it equal to the momentum of a photon of same energy? For the photon, because it's a wave, electromagnetic wave, till now, it's like a classical picture. Because it's an electromagnetic wave, how do you compute the momentum? You compute it just like in terms of the wavelength. Okay. How do you know the wavelength? You can compute the wavelength by hc over energy. You know the energy, which is 2 electron volt. You put it here, you get the momentum of photon. Now for the momentum of electron, it can be computed as under root of twice m into energy of electrons. Simple as that. And what happens? You put in the values of energy. You put in the mass of the electron 9.1 to 10 to the power minus 31 kgs. Energy of the electrons. You can keep it in electron volt or you can convert it into joules. When you do it, you get that this particular electron's momentum is much greater than the momentum of the photon of the same energy. And this momentum is very small. It's of the order of 10 to the power minus 27 values, the units of the momentum. What are the units of momentum? P is m times v. So this is kilogram meter per second. This is kilogram meter per second. Yeah. So you will see that the photon momentum is very small compared to that of the electron momentum. That is what I was initially talking about. Because the photon is a quasi particle. It's just like a field that is propagating the information between the two actual particles. Okay. And let's say, for example, some of you might be knowing about the direct band gap and indirect band gap semiconductors. So the direct band gap semiconductor is where the conduction band minima and the valence band maxima are at the same K point. Same K point. This is something called as direct band gap semiconductor. And it happens that if you irradiate with light, the electron can go from this region to directly to the conduction band. Okay. But the question is, why doesn't the electron go this way? Why does it directly go up in energy? Why doesn't it change the K when you shine the light? The answer is also fascinating. It is related to because the photon imparts very small momentum to the electrons. Okay, if you consider this as a photon and if you consider this as electron, if hypothetically as a kind of understanding, if you consider that the photon is hitting the electrons just like a ball, because the photon is having very small momentum, it's not able to change the momentum of the electrons, although it just changes the energy of the electrons. That is the essential notion from this. Photon gives its energy to the electrons, but doesn't change the momentum. Otherwise, electron would have gone in the different direction altogether. That is what basically happens. But in certain instances, you can even tune it. You can change the direction of the electron with photon. That's a different story altogether. But that is the essential picture. So you have to just solve it using certain basic equations. Now, another easy question is that when light travels in a time invariant medium, what is time invariant medium? It is a medium which does not change with time, where there is no time dependent thing changing. Just like if you have water and if you have air, if you have a wave going in, it will refract and then it will come back on the other side of the water. Let's say this is a water slab. If there is nothing changing with time inside the medium water, then there is only one thing that is going to change in the electromagnetic wave, that is basically the wavelength. The other things are not going to change. Okay, and let me just give you an. So what is basically going to happen? That is the fundamental notion from basically the simulations, what you saw in these. When the plane wave hits the some different refractive index medium, its wavelength goes on changing. The frequency doesn't change because it's dependent on the source. And wavelength is basically a space concept. The frequency is like a temporal concept. But you can have temporal frequency as well as spatial frequency. That is what Professor has already talked about. So the essential thing is that if there is nothing changing inside the system, if it is LTI system. In control systems, mostly people talk about LTI systems, linear time invariant systems. Okay, if there is nothing changing with respect to the time, then only the wavelength is going to change. But if you have something going inside the medium, let's say if you have a water, if you shine a beam of light like this, it goes like this and it comes on the other side. If you don't have LTI system, if you have time varying system, let's say on this water slab, let's say if this was a water slab, if you somehow put maybe some sound source over here, which is emitting acoustic waves. Those acoustic waves go into the water, and now it's no longer a LTI system because these acoustic waves are time varying waves. These are plane waves, but these are acoustic waves, and they are moving inside the water. That is perturbing, that is disturbing the water, and you no longer expect that only the wavelength is going to change. What is sometimes going to happen is that you can get a different spectrum of the frequencies altogether. And this is mostly, this process phenomena is basically used in modulators, something called as acousto-optic modulators. Acousto-optic modulators. Oh God, cancel this down. Acousto-optic modulators, wherein you can tune the wave, you can tune the, I should say, light with the help of acoustic wave going inside the medium. You can see that once the acoustic wave goes, it will diffract and you will have different orders of diffraction and you can get all other sorts of phenomena. These are called as modulators, where you can modulate the, I should say, uh, the the light beam using certain time dependent sources, which can be a sound source, which can be even electric field. If you apply some positive and negative, that is also going to be time dependent thing. Okay. Now another question here is about the dispersion curves. If you have an omega versus k of an electromagnetic wave in a free space and in the medium, what are the relations between Km and K0? So these are the red one is the dispersion in the free space, the blue one is the dispersion in the medium. So you have to give the relation between K naught and Km. So this is 0.2, this is 0.1. So you know, for let's say for example for medium 1, you can write omega as C times K naught. But omega is given, that is how much is it? 1 is equivalent to C times K naught. Okay. For the blue one, you have 2 equals to omega times sorry, c times km, but this is divided by n because there is a refractive index now. And how much is the refractive index? You have 2 equals to ck times 1.5. So you can write ckm 3 over 2. So 2 goes. This will be 3 equals to ckm. So now you can use a simple relation. You can take the ratio of these two and you get km to be equivalent to 3 times k naught. So this is the exact value. Just simple understanding of that the frequency, angular frequency is speed times the wave vector of the light. Okay, in space, free space, but in medium it is basically k divided by n medium. That is as simple as that. Because this k is basically a wave vector and it's given by 2 pi over wavelength. And you saw that what happens to wavelength, it changes. Okay, and if this is k in free space, then k in medium will be 2 pi lambda over n. So it will be 2 pi n over lambda medium. This is medium. This is k medium. So accordingly, you can arrive at this particular relation. It's just as simple as that. Quite simplified relations. Now, what is next? Okay, this we have been, I should say, studying from the class 12th itself. So we have to just match the following. So you know this particular thing is, it's like Gauss's law in electrostatics because del dot D is the charge density. What is D? It's the, I should say, electric vector potential and or I should say displacement potential, electric field displacement. And electric field displacement vector is basically epsilon times the electric field. If you have the free space, if you don't have a, if you don't consider the polarization, otherwise there is some polarization component also. And if you write it in terms of electric field, you can write it as epsilon del dot E equals to rho. So you get del dot E equals to rho over epsilon. So this is basically the Gauss's law. Okay, and that is the same equation which basically simplifies to Poisson equation. In one dimension, you write the Poisson equation like this. This Poisson equation is a lot used in the device physics. Comes from the similar. These are just a similar set of equations. So this is the Gauss's law. This is the another one is the Faraday's laws of the Gauss's law of electrostatics is this one. So one goes to C. So there is only one part where one goes to C. I guess that should be the answer of this question. So this one is the Gauss's law of magnetostatics. This one is the Faraday's law of electromagnetism. And this one is the Ampere's Maxwell law. And yeah, that is it. Okay, that's as simple as that. Okay, let's move on to the other question. Which of the following factors influence the resolution of an optical lithography system? So what is this resolution? Resolution means that how well an optical system, let's say a camera, how well a camera is able to resolve two objects which are closer to each other. Let's say you have a phone and you have a camera over it, and let's say you have two objects, and at this particular distance, the camera is able to resolve them properly. You can see two objects on the picture clearly. As you bring these two objects closer to the camera, you will see that at some particular distance, the camera won't be able to resolve them separately, and it will appear as a single, maybe a merged or a blurred thing. So that is basically the resolving power of an optical instrument. Similarly, it was mostly used in earlier in telescopes because they were the most earlier instruments for the optical instruments. So if you have stars and the stars are very far away from each other, but because on the Earth you are looking at using some telescope. Let's say for example this is telescope, and the light is coming from these stars. What happens is that the resolving power of a telescope is that how well a telescope is able to resolve that these two objects are separate and not a single object. So that is basically the resolving power of a telescope or any other optical instrument. Even a microscope, how well a microscope is able to resolve two nanostructures well. And it mostly happens, how well it can resolve basically depends upon the wavelength, which wavelength you are using to view those objects. And if the wavelength goes on reducing, you can resolve smaller and smaller objects. Okay, it basically boils down to the diffraction. So once any object size, let's say this is a ball of the size of d, diameter d. If the diameter d approaches the wavelength of light, then there will be some phenomena like diffractions and other phenomena which will happen. Okay, light will start to diffract. Because of it will become difficult for our eyes to see this ball. Okay, but let's say for example you have a ball of size d and you are viewing it at using, let's say for example, 500 nanometer light, which is approximately maybe some, let's say for example, 800 nanometer light, which is a red wavelength. And let's say the size of the ball here is maybe 1 micron, which is greater than the wavelength. So you can clearly see the ball with your eyes even, but or any of the optical instrument. But what happens if you have another ball, if you have the same wavelength coming in, but you have a ball of the smaller size. Now this time D is approximately 500 nanometers. What you're going to see is that the D is less than lambda. You no longer will be able to see this particular ball because there will be diffraction of the waves, because the size of this particular object is now much smaller than the wavelength, okay, of the light you are using to view it. Okay, so now the light wave beams will diffract and you no longer will be able to sharply see this particular object. So this is basically called as diffraction limit. And this particular resolution as well depends upon this diffraction limit. It also depends upon the numerical aperture. Numerical aperture is basically how much a lens is able to gather the light. So if there's a huge lens, it's able to gather a lot of light. So its numerical aperture is large. If you have a smaller lens, its numerical aperture is smaller. It also depends upon other factors, but this is just a layman term. So if you have a huge lens, you can resolve the two objects clearly. Okay. On the other hand, if you have a smaller one, that brings in its own challenge. So now what happens is the resolution of an optical system. Let's not talk about lithography system right now because sir professor might have discussed about it. So resolution of optical system depends upon wavelength, it depends upon numerical, it depends upon the empirical constant. This is some constant. Let's forget about it. Basically, it depends upon all of the above. Okay. So empirical constant is some kind of a constant parameter which might be multiplied with it in order to get something else. Let's not talk about it, but it's basically a process related factor. Process related factor means that how the lens is made, what material is this lens made up of, whether it's a large band gap or what is the band gap of material, what are the other constituents of the lens. All of those properties are summed up in a constant, which is basically an empirical constant, and it's just a constant factor. Okay, that is the resolving power of an optical instrument. Now, if you consider the question number 7, what happens to a wave if it's moving a wavelength of 400 nanometers, moving and hits the glass of thickness of 1000 nanometers in the direction surface normal. It hits at a normal angle. So if this is a slab, it hits at a normal angle. You know that outside the amplitude will be large and then it will decay inside it. And then it will come back outside as it is. So as per that phenomena, you should have the answer as C. Because here nothing is happening to the amplitude. Here the amplitude is increasing, which is not possible inside water. At least inside water, it's not possible. It is this particular phenomena which is shown in B. It can be possible if you replace the middle water slab with something called as active medium, which is basically used in laser amplification. Let's not talk about it. But this can be possible. Active medium is some medium where you can have stimulated emission. Stimulated emission, wherein let's say for example this is some atomic level and this is some other atomic level, and if the electron goes to this higher level, all of the electrons, and if all of the electrons decay to the ground state simultaneously, they can give rise to photons, many photons, and those many photons basically cause amplification of the electromagnetic wave. This is basically the phenomenon of laser or lasing. So this can be possible if the middle water slab is replaced by an active medium, just like inside the laser. But right now, that's not the question here. Similarly, this is the part which I'm basically talking about. It's decaying inside the medium. The amplitude is reducing, and then it's coming out back. But for this medium, this is also not possible. So this is the D slab. This is the thickness of the slab. Okay. And now, moving to question number 8. If the wave number of an electromagnetic wave is given, wave number is basically K. It is given as 500 per centimeter. We need to find the energy. It's also simple. If you know the wave number, you can compute the wavelength. Okay. And note here, it is in free space. If it was not in free space, then they would have mentioned the refractive index also. Okay. But you have to consider here it as a free space and consider n equals to 1. So k is equal to 2 pi by lambda. You get lambda equals to 2 pi by k. Once you get the lambda, you can compute the what do you need to compute? The energy of the electromagnetic wave in terms of the electron volts. Okay, so you have E equals to hc over lambda. So you know the lambda, you know the velocity of light, you can compute the energy. You get around 62 milli electron volts. That is basically 0.062 electron volts. As simple as that. This is the easiest problem. Now, again, a beam of light, for example, is incident on an air glass interface on the from the air side. What is the wavelength of light in the glass of refractive index 1.5? So you have a air, you have glass, you have waves coming in with certain wavelength of 642 nanometer. What's going to happen to the wavelength inside? The wavelength is going to reduce by the factor of refractive index. So wavelength inside the medium is equal to wavelength inside free space divided by the refractive index of the medium. That is what we have been talking about. The wavelength reduces. So the wavelength in the medium will be 642 nanometers divided by 1.5. That is 642 divided by 3 into 2. How much is it? I guess this is 332, 31, 34, 248, 24. That is 428 nanometers. This is the answer of this question. Again, the simpler one. So the question 10, this is related to the band gaps now. So for example, if you have a system 1, you have system 2. For example, this band gap is large. Large compared to what? Compared to the incoming electromagnetic waves energy, h nu. For example, this band gap is, let's say, 9 electron volt. And this band gap is, let's say, 1 electron volt. If you have an incoming wave, electromagnetic wave with photon energy of 2 electron volts, that this particular electromagnetic wave which is coming with 2 electron volts will not get absorbed in it. It will just pass through. That is what basically a transparent material is. Okay. If the energy gap, which is the electronic energy gap, if that energy gap is larger than the incoming photon, then the photon just goes passes through it. It doesn't interact with it. It doesn't get absorbed with it. It doesn't cause electron transitions. But on the other hand, if 2 electron volt photon comes in and hits this particular medium, it will get absorbed and it will bring the electron to the higher energy levels. That is the concept of basically absorption. So if this energy value is of the order of band gap, then it's going to get absorbed. Just like I should say the notion of photoelectric effect. But in case of the photoelectric effect, you had something called as work function. So you talked about that if the energy of the photon is much greater than the work function of the metal, let's say, work function of any system, then at that particular point there will be the electrons will be knocked out from the system. That means there will be interaction, or the electrons will be absorbed, the photons will be absorbed, and the electrons will be knocked out. That is basically the photoelectric effect. But if you have the energy less than the work function, those photons cannot knock out the electrons. For those photons, the medium will behave as a transparent. That is the same notion. So which are the correct ones here? So the glass appears transparent as its band gap is 9 electron volt and all the visible light passes through it. That is absolutely correct because the visible light is from 400 nanometers to 800 nanometers. And if you convert it into electron volts, it will be around, I guess, maybe how much is this? Maybe around 1 electron volt or even less when you convert it into electron volts. And 9 electron volt is much, much greater than 1 electron volt. As a result, if you have a glass, whenever the light comes, it just goes through the glass. Why? Because the band gap is so huge that none of the photon is going to interact with the electron or get absorbed or create any transitions. That is as simple as that. And the silicon appears black as its band gap is 1.1 and all the visible light passes through it. No, silicon appears black because its band gap is this and visible light gets absorbed. This is the exact answer. You see that you have a glass. That means if you have an electromagnetic wave coming, that is just passed through the glass because the band gap of glass, which is basically silicon dioxide, is 9 electron volt and it is much much greater than 1 electron volt. But for the silicon, if you have a silicon with a band gap of let's say 1.1 electron volt, and if you have incoming light beam of let's say 1.77 eV, this is basically the range given 1.77 to 3.1 eV. So this is 1.77 to 3.1 eV. So 3.1 is basically this is 3.1 eV, this is 1.77 eV. So if you have 1.77 eV photon coming in, that will get absorbed, that will cause the electronic transition inside the system. One photon just creates the electronic transition of the one electron. Okay. And we say that one electron hole pair is generated. So if you have a photon coming in, the electron will go from this to this. You have an electron in the conduction band, you have a hole in the valence band. And I'm talking about silicon, which is a semiconductor. This you might have all studied about in the previous sessions in the device physics. So these are the two answers of this particular problem, and that is it. We are done with the today's session. Uh, some simpler problems, but mostly main thing is about understanding where you can relate the electrons behavior and the photons behavior in both of these systems. So that is the essential part. So in the next lecture, in the next session, we will be mostly solving questions on light matter interactions. I'll try to keep the introductory or the basic part very small so that we can mostly spend our time on the question answer session. Although I try to solve and all of the questions in a well stipulated time. So we will be meeting in the next lecture on next Wednesday or next Saturday at the same time. So if you have any questions, you can stay or you can just post it anytime. Or if you have any queries, you can just tell me. Otherwise, we are done with the today's session.
Just a clarification regarding the assignment submission.
Sorry, say it again.
I just wanted a clarification regarding the assignment submission.
Yes, yes, tell me.
It week one and week two submission date is due on 6th of August.
Okay.
So, why is it that both weeks are given on the same day?
6th of August is Wednesday. Which both weeks are you talking about?
Week one and week two.
Oh, okay. I got it. So there's a next session on 2nd August, right?
Yeah.
Hmm. To be honest, I am not aware about that particular thing because I don't mostly deal with the submissions or other things. You can directly just text the NPTEL team, whoever might be coordinating with you. You can just drop a mail to them
Okay.
or you can even drop a mail to professor, uh, or the NPTEL team will be better if you have some contact given in the NPTEL team. They might be able to answer your query. Okay.
Okay.
Okay. Thank you.
Thank you.